Okay, so we've been talking about fields a lot, magnetic fields. Let's finally bring into it what's kind of been the elephant in the room this whole time, the force, the magnetic force that's actually been causing these things to happen that we've been seeing happen, right? Like when a magnet deflects, things don't move, they don't accelerate, at least without a force acting on them, right? So there must be some kind of force at play here. Let's actually get into what the magnetic force is about and how we can analyze that. Okay, so it says here if a current, it doesn't mean if as like if it does or doesn't, it might not. No, it does. We know it does. We proved it, right? It's saying more like since a current does, or because, right? It's not a matter of if. A current does produce a magnetic field. We've seen that, okay? We've proven it. So because a current produces a magnetic field, it will behave as a magnet, right? As soon as you have a magnetic field, that thing's now a magnet and is thus attracted or repelled by other magnets, okay? Or it might attract metals, okay? Not all metals though. Ferromagnetic metals, right? Ferromagnetic metals, right? Not any old metal. It won't attract aluminum, for example. Okay, it needs to be ferromagnetic, which we talked about before. So two magnetic fields interacting will create a force, right? So you know this, right? When we put the bar magnets together, okay, what happened to them if they were lined up like this, for example? Okay, if they were close enough together, they would accelerate. And as we know from physics 20 and from all of our physics, right? If something is accelerating, there must be a force acting on it. You can't have something go from being at rest to in motion without a force being involved in some way. Okay, so when we placed those two magnetic fields near each other, they interacted in such a way that an attractive force was produced. So now keep that in mind. Two magnetic fields interacting, right, will create a force. It doesn't seem that weird here, okay, but it's going to get a little bit weirder when we think about the magnetic field induced by a current, or at least at first it might seem weird, okay? So it's time for our first kind of equation here, right? We have that. We haven't had one yet in chapter 12 for magnetism, okay? So the magnitude of the force is given by either F equals QV, we'll talk about that little symbol in a sec, or QVB, sorry, remember B is the magnetic field, or F equals ILB, okay? And these are indeed magnitudes, okay? These are magnitudes of the magnetic field. Okay, so when would you use each one? Well, what is I? Remember, I is current, okay? So I would use, you could keep calling this the force. What is the kind of label for the force? It's Fm for the magnetic force. So Fm equals I, current again, L, again, there's that little symbol, E. Okay, when should you use that guy? Well, in the context of current and this thing here, okay, this little L, we are talking about a charge that's in a wire, okay? So I'll get to what each variable means here in a sec. I, of course, is current, right? So I is current, okay? L is going to be, it literally means the length of the wire, okay? So length of wire with an important distinction that symbol is going to involve, okay? And then, of course, B is our magnetic field, okay? So since we're talking about current and a wire, okay, this is going to be, we would use this thing, okay? Use this thing when our moving charges are confined to a wire, okay? Because of that fact that we're talking about a length of wire and a current, okay? This kind of means we're going to do it when moving charges are confined to a wire. Now, technically, this doesn't only apply in a wire, right? L is just the length that it travels through a magnetic field, and I is just coulombs per second, so it doesn't have to be in a wire, but this is kind of always when it ends up making sense. We also have Fm equals Q. The magnetic force equals QVB. Okay, what is Q? Q is still charge. Okay, V, and again, you see that symbol. Okay, that's going to be important. Speed. Okay, and again, B, nothing different there. That's still our magnetic field. Okay, so when do we use this one? We use this one. Notice how there's nothing about the length of a wire. It's just talking about the speed of some charge. So this is when our charge is free to move. Okay, to move through the magnetic field. Okay, I just really want to quickly prove to you that these are not so different. Okay, they kind of come from the same place. So I'm going to start with this equation here, just off to the side. I have that Fm equals I L B. Okay, what is I? How do we get current? Well, current is charge per unit time. So Q over T times some length that's traveling through the wire times B. Okay, hang on. Do you see this? Some length that's traveling through the wire and the amount of time it took it to go through the wire. Hey, how far it went divided by how long it took. Does that sound like something? A distance divided by a time. So what is this? This is just Q V B. So they really are the same idea. One just makes more sense when we're talking about a current carrying conductor, and one makes more sense when we're talking about a free charge moving through a magnetic field. Okay, so I just wanted to point that out, that these aren't very different ideas. They're the same idea, just applied in more convenient ways depending on the situation. Okay, now I've been holding off on this, and it's crucial. What do these symbols mean? Okay, you might recognize those. They mean, okay, the magnetic force only comes from the component of the speed or the component of the wire length that is perpendicular to the magnetic field. Okay, perpendicular to the magnetic field. So only the perpendicular component, actually counts towards creating a force. So only M. So if it's going super, super fast, great, but only the perpendicular part of its motion is actually going to end up mattering. So what do I mean by that? If you have some magnetic field, okay, and you have some velocity that it's coming in with, some charge is coming in with some velocity, that's just its V, okay, it has some component that is perpendicular to the magnetic field itself. So when we go to calculate it's the magnetic force it's going to feel because of the magnetic field, right? We are not going to use V. We are going to use only the perpendicular component. Only the perpendicular component. So with this being the angle of entry or the angle of incidence, see how this is the angle that it enters the B field at, right? V, in this case, V perpendicular equals V sine theta. Okay, so great that it's going fast this way, but that doesn't count. Okay, this Y component, this parallel component, V parallel, does not count at all. Only this will contribute to the magnetic force. Okay, then it asks us to figure out, hey, what are the base units of magnetic field? We have been talking about the magnetic field, but we haven't had to do any calculations with it yet. So we've kind of dodged the conversation of units. No longer can we do that. Let's go ahead and figure it out. Well, Fm equals, I'm going to do IL perpendicular, so only the perpendicular component of the wire, only the amount of the length of the wire that travels perpendicular to the magnetic field counts here. And so rearranging, magnetic field, divide both sides by IL perpendicular equals Fm over IL perpendicular. Okay, so what are the units of a magnetic force? Just like every other force in the universe, the units are newtons. Okay, divided by, hey, what are the units of current? Amps. And what are the units of a length? Meters. So we have newtons per amp meter. Okay, we can probably simplify this a bit more. So let's see. Newtons we know as a kilogram meter per second squared. Okay, not that we probably can, we actually have to because it asks for the base units. Newtons are not a base unit. Okay, kilogram meter per second squared. Amps actually are a base unit, but I know there's seconds here, so we can probably simplify a bit. If we do, whoops, not coulomb seconds, coulombs per second, okay, times meters. I'm just going to go ahead and put these all in square brackets to remind us that we're just doing unit analysis. Okay, that's kind of how we show unit analysis. All right, so still just trying to simplify this out, get our base unit. So now we have kilogram meters per second squared over coulombs per second times meters. I'm just going to defractionify everything. So what I mean by that is if it's being divided, I'm going to put it down. If it's being divided in a denominator, I'll put it up. So kilograms meters, okay, the second squares belongs in the denominator, right, per second squared. But then we have coulombs per second, but that's a denominator in a denominator, right? So dividing by coulombs per second is the same as multiplying by seconds per coulomb. So that seconds actually gets put up there, and then meters. Okay, let's just do some cancellations. Seconds over seconds squared, so the squared's gone, but we still have seconds in the bottom. Then meters and meters. Okay, there we go. So what is the unit of magnetic field? It is a kilogram per coulomb second. Now, we got kind of sick of calling it that, and so we named them after a very famous physicist who worked a lot with electricity and magnetism by the name of Nikola Tesla. So the unit of magnetism, the standard international unit of magnetism, is the T for the Tesla. Okay, might be more famous now as a car, but Elon Musk actually named the Tesla after Tesla as well. Okay, I'll challenge you to use the other formula, right? Try using that one to derive the same unit. See if you can get the kilogram per coulomb second for that guy as well. We are actually, I'm just going to skip this because it's kind of lying to you a little bit. So the magnetic force does not actually follow an inverse square law, at least practically in our world. As we know, all magnets have a north and south pole, right? And as we learned, you can't split them up. You can't break a magnet in half and end up with, oh, this piece is all north pole and this piece is all south pole, right? They'll immediately just make a new south pole and a new north pole so that you have two magnets with two north poles and two south poles, okay? However, there is a theoretical particle. It would actually be an elementary particle like an electron, okay? It is yet to be discovered. It's only been postulated in particle physics. That is called a magnetic monopole, okay? And if there was such a particle, a magnetic monopole, it would only have one pole. It would be a elementary fundamental particle, okay? Now, if it existed, its magnetic force would follow an inverse square law, where as you decrease your distance away from it, it falls off as 1 over r squared, okay? However, no real magnets that we deal with, no magnet that we've actually found besides this theoretical one, does quite follow an inverse square rule. It actually follows an inverse cube rule, okay? I want to be clear, this is way beyond what you need to know for the course Physics 30. I'm just kind of giving you some insight. So does it fall off quickly? Yes. Does it fall off faster than linearly? Yes. That's what you need to know for magnetic field. Okay, it's not quite an inverse square law, but it does fall off quickly and faster than linearly. Okay, exponentially inverse relationship between magnetic force and separation distance. Okay, so an electron is moving at 75% the speed of light when it enters a magnetic field with a magnitude of 0.35 Tesla. Okay, we're going to have our B field, our magnetic field. Okay, this is B, our magnetic field. And an electron is moving at 75% the speed of light when it enters a magnetic field. So it's moving at V equals 0.75 C. And it enters, at first, we're going to figure out what happens if the angle it enters at is 90 degrees. In other words, if it's perfectly perpendicular, okay? Okay, question for you. What makes the most sense to use here? ILB or QVB? Well, this is a free electron, right? So it makes the most sense to just say, hey, what's the velocity of the electron? Not to think about the current flowing through a wire per second. So I'm going to use QVB. Hey, especially since we have a V, probably makes sense to use QVB, right? Okay, so it's moving at 75% the speed of light. What is the vertical component of its velocity? Well, it's all of it. We can think of its entry angle as 90 degrees, right? And as we showed up here, how do you get the perpendicular component if you know its entry angle? Well, you do sine theta. Hey, type really quick, or maybe you know this from your math class. Sine of 90 degrees equals 1, right? So we could even put that in. Fm equals Q V sine theta, where theta is the entry angle, okay, in this case, 90 degrees, V sine theta, because that's V perpendicular, times the magnetic field magnitude. And we have that these are all magnitudes as well. The magnitude of the magnetic force is going to be, what's the charge of an electron? It's E times 10 to the negative 19 coulombs. V sine theta, so you can take 0.75. C is on the back of your periodic table. It's the speed of light in a vacuum. Okay, you'll get to know that number very well, especially next unit. 3 times 10 to the 8 meters per second is that, 300,000 kilometers per second. 0.7 sine 90. Again, being kind of facetious here by even putting that in because it's going to be 1, but it doesn't hurt to show you what I mean, times 0.35 Tesla, which as we know are kilograms per coulomb second. If we want to check really quick, we're going to have kilograms per coulomb, okay? So kilograms per coulomb second, so the coulombs would be gone, right? And then coulomb second, so the seconds would get squared. And then we have kilograms meters per second squared with the coulombs gone. Hey, kilogram meter per second squared, that's a Newton. So Fm, magnitude of the magnetic force, I got 1.26 times 10 to the negative 11 newtons. Cool. Great. You're saying, okay, what's the direction? You're going to have to wait for another hand rule for that. Okay, now it's saying, what if, so we'll call this A, okay? Now in B, what if it enters at 45 degrees? So now its entry angle is not 90. Now in B, its angle of entry is 45. So now in B, this is 45 degrees. Where is its component of its velocity that is perpendicular to the magnetic field? Well, you can probably see it, right? It's not this component. That would be parallel. It's this component. So that is V perpendicular, right? That's V parallel, which counts for nothing. If it enters at 45 degrees, how do we get? So again, we're just starting here. Fm equals Q, the charge, times the perpendicular component of its velocity, times the magnitude of the magnetic field. Now we're actually not just being silly by putting it in, or I guess being sticklers by putting it in. We actually need to say that that equals Q times V sine theta, okay, times the magnetic field strength, which is going to be 1.6 times 10 to the negative 19 coulombs, okay, times V is still 75% the speed of light, so still 0.75 times 3 times 10 to the 8 meters per second. Sine theta, though, now is not just going to be sine 90 and be 1. It's going to be sine of 45 degrees and be 1/2, okay, times the magnetic field strength, which is 0.35 Tesla. All right, multiply that all out. What do you get? The magnetic field strength, if it comes in at 45 degrees, is going to be 8.91 times 10 to the negative, times 10 to the negative 12 newtons. Oops, and I apologize. I think I said sine 45 was 1/2. I'm thinking of sine 30. Sine 45 is 1/√2. Sorry. Just noticed, by the way, too, whoops, I was only supposed to have how many sig digs? 2, right? 2. Okay. Finally, what if its angle of entry now is 0 degrees? So the angle between the magnetic field and it is now going to be 0 degrees. What does that mean that it comes in looking like? Well, how do I make this angle 0 degrees? I keep making this smaller and smaller and smaller, right? So I'm going to show you over here. If it enters at 0 degrees, it enters perfectly parallel, right? Two lines that have an angle between each other of 0 degrees, well, those are parallel lines, okay? So now, what's V perpendicular? What's the perpendicular component of its entry speed? Well, it's 0, right? If you can kind of tell from looking at it. Or we could also tell ourselves what's sine of 0? Well, you might know from math class, sine of 0 is 0. So Again, Fm, the magnetic force, is going to be equal to Q times the perpendicular component of its velocity times the magnetic field strength equals, if we want, we could just say now that the perpendicular component is 0, but if we want to be really rigorous, we could say Q equals V sine theta times B, which is 1.6 times 10 to the negative 19 coulombs, times still 75% the speed of light in a vacuum. Okay, this electron's going pretty quick. Times sine theta, so sine of 0, which again is going to be 0, times B, 0.35 Tesla. And if you want to check my work and plug it in your calculator, you can, but I'm telling you, it's going to be 0 newtons. So this thing will feel no force if it does not have a perpendicular component. This seems kind of weird, doesn't it? Well, electromagnetism can be kind of weird at first. So in order to feel a magnetic force, some moving charge, whether it's in a wire or not, needs to have a component of its velocity that is perpendicular to the magnetic field it is moving through. Okay, now I get that it can seem kind of weird at first why this magnetic force is perpendicular to not only the speed of the moving charge, but particularly the external magnetic field. If you are okay to just accept that it is, then you could just skip past this part. But for those of you that will not sleep tonight, unless you can kind of see why, or at least have a bit of a conception why, okay, let's just imagine a scenario, okay? So I'm going to take kind of that same field as before. So this field here, okay, now we're going to look at it from down here. So now our eye is in the paper kind of looking this way at it. So we're just going to actually draw the magnets causing the field just to help us visualize this. So if we have here, so I have here two kind of magnets, a north pole and a south pole that are of course going to have a magnetic field between them. That's going to be our external magnetic field. And what are we going to do? Let's send an electron. So let's send an electron into the page through that external magnetic field. So let's think about the field lines. The external field here, what are they going to look like between these two? Well, they're going to be leaving north, entering south, right? Leaving north, entering south. Now, I just told you this electron is moving. It's going into the page. So it's an electron, negative charge. Take your left hand and figure out what the magnetic field that it induces is going to look like. So if you put your left thumb into the page, you'll notice that your fingers curl this way, right? So there is the magnetic field induced by that thing's moving charge. And so what we're saying here is that, okay, the interaction between the magnetic field induced by the moving electron and the external magnetic field, okay, are going to cause a force that is perpendicular to both of those directions. So if you think about it, okay, we have this going this way, right? We have this going side to side horizontally. So I'm going to use something that's kind of called the replacement magnet method, and all that does is help us visualize what kinds of interactions are going on here. So I'm going to take this is a magnetic field this way, right? But we can kind of say, okay, if this is magnetic field is going this way, it's like there's a smaller magnet here, right? With a magnetic field traveling through it that has it's entering south, right? Magnetic field lines would enter south and they would leave north, okay? Now down here, same thing. Where would field lines go? They would enter south and leave north. Okay, with that so far? Now let's look at what about on our induced magnetic field from our electron? Well, we would have, this one's going this way. Okay, easy enough. So at this top point here, what could we replace that with? What would the magnetic field look like if we had a bar magnet here? Or how could we use a bar magnet to produce the same magnetic field that we see induced at that point? Well, it would, right, if it's traveling kind of to the left of your screen, it would enter south and leave north. Okay, now let's do the same down here. Enter south, and leave north. So what is the resulting is we just use if we kind of think about it as replacement magnets, what kind of force would these two magnets feel? And what kind of force would these two magnets feel? The two kind of replacement magnets that are closer to each other, right? So again, this is just the magnet that if I placed there, I would end up with kind of the same field, right? because that's what we're looking at is the field. Same thing here. If I put this magnet here, I would end up with the field looking the same, and same here, and same here. But again, what would these feel? Well, would they feel attraction or repulsion? You've got a north next to a south and a south next to a north. So these are going to feel attraction. Which way? Up towards the top of your page. Which way would these feel? They would feel repulsion, right? North, north, south, south. They would push this charge up again towards the top of your page. So when you have your electron going into the page, okay, you have your magnetic field going left to right, and what's the resultant magnetic force? Up. So we kind of have three things that are all perpendicular to each other. If we wanted to visualize this on like an X, Y, Z axis, we would have our Y going side to side. That would be our magnetic field, right? We would have our force magnetic going straight up. Okay, that's Fm. And how do we show on it? You might not have seen an XYZ axis before, okay, but how do we show something going away from us on this is actually, it gets called the x-axis, the way I'm going to draw it. That is the V, right? So, okay, so that kind of replacement method should at least help to ease your concerns about why is this force perpendicular? We are going to now really jump into the third hand rule, but I want you to come back to this after we've done the third hand rule, take a look at it again and see if it agrees or not. So just to provide a quick visual, because I know you might not, of what you just saw, you might not have actually ever seen an XYZ axis before. It's a little weird to look at first. So what is this actually showing? So it's kind of showing the V is going away from you on what's usually called the X-axis in these. The magnetic field, this is usually called the Y-axis, and then the FM is actually called the Z-axis. So the Z-axis is straight up and down. There's that. As we know, the electron was moving away from us, okay? So we kind of say it's going away like that, right? Going away like that. And then our magnetic field would be off to the right. So what it ends up looking like is this, right? This is all that's showing. Okay, so they are perpendicular to one another, right? Force and velocity are perpendicular, field and force are perpendicular to each other, and then velocity and field are perpendicular to each other. Three things perpendicular. Okay, so just again, another visualization. They've chosen to label it differently a bit here, and the colors are different, but right, this kind of is better than I could draw it. So you have your, in ours, this would have been the magnetic field off this way, perpendicular, of course, 90 degrees to where our magnetic force was up to the top of the page, and then our velocity would be along what they call the negative z-axis here into the plane of the page. So how can you keep these three mutually perpendicular directions all straight? Well, luckily, there are two things on the ends of your arms that can point in three perpendicular directions at once. Okay, so let's learn. So it's time for a new hand rule. Now, because we are dealing with, again, perpendicularity here, okay, we are going to need a hand rule. The third hand rule, okay? Now, the big difference between the first two hand rules and the third hand rule is that in the first two hand rules, we were always kind of talking about a charge and a magnetic field that matched each other, right? So we were talking about a moving charge and the magnetic field it induced. Might have been circular, might have been straight, but either way, it was one charge and the magnetic field it induced. In the case of our third hand rule, okay, we are talking this B field, this magnetic field does not actually belong to the moving charge. This is an external magnetic field. So one that did not come, it's not induced by the charge. It was already there. Okay, it's external to the charge, like the one we were looking at before. We will, again, I'll print off some big pictures and we can do it over camera so you can actually see me, because me talking about a hand rule is hard to wrap your head around. But first, let me just get the rules down. Okay, we use the third hand rule for a force created by a magnetic field that is perpendicular, okay, must be perpendicular to a moving charge. Okay, so this is kind of the first time you've had to deal with a force that works this way. You've never had a force that acted perpendicular to the field which caused it. Never. The closest we've gotten to even that is in an electric field, you could have a force in the opposite direction, so anti-parallel to the field lines, right? How would you get that? Well, with a negative charge in an electric field, it will move in the direction opposite of the field lines, because electric field is defined as what a positive would do, right? But nothing was ever this weird. Nothing was perpendicular to the field. And again, that has to do with the interactions between the induced magnetic field and the pre-existing external magnetic field. okay? So your fingers in the third hand rule are in the direction of the magnetic field, okay? Your fingers are in the direction of the magnetic field. And then your thumb, okay, just like in our first hand rule here, your thumb points in the direction of the moving charge. So what do you think? Which hand are you going to use if the moving charge is negative? Okay, you guessed it. If the moving charge is negative, use your left hand. Okay, again, left thumb if the moving charge is negative. Whoops. Okay, so left for negative charges, left hand, but obviously your left thumb too. Okay, right for positive charges. Okay, so this third hand rule actually kind of applies sort of the same for your fingers and your thumb. It's the same as the first hand rule. The difference is though this magnetic field is not induced. It's the external one. But like the first hand rule, thumb is the direction of the charge motion and fingers are the magnetic field. Okay. Your palm, and I like this one, this is what I like about this one, your palm shows the direction of the magnetic force. And when I actually get on camera and show you, you'll see, but it's like a push, right? A force is a push, so your palm is actually going to push in the direction of the magnetic force that results from this charge moving in a field, okay? There is a bit of a trick that some people use. Honestly, I don't think of it because to me it makes sense. You got your field, your fingers, you got your charge moving along your thumb, and then you push with your force. But some people like to remember FBI for they go from palm, fingers to thumb, palm, fingers, thumb. It goes FBI. I have a problem with it though. It's only I on one hand, right? Which hand is it I? Remember, I is current, okay? Which leads me to my big problem with this picture. Do you see it? Sticks out like a sore thumb. Okay, this thumb should not be current. Why? Because what hand does it belong to? This is a left hand. This is a left hand. Why are they showing current with their left hand? Okay, so make that note for yourself. They should not be using their left hand for this. If they're either that or this should be electron flow, not current. Okay, so if this is left hand rule, okay, if they're using their left hand rule, let's just say current, this is a left hand. So should be electron flow. Okay, this is a bad picture. But the force I agree with, okay, so if this was electron flow, then this is the direction that a negative charge would feel. So if you had a magnetic field along the axis of your fingers and your electron, or I guess it doesn't have to be an electron, any negative charge was going this way, then your force would be up that way. Okay, so again, hand rules are cool and all, but let's not just jump into them until we've kind of proven them with something physical, right? Or at least built some confidence with it. Seeing is believing, right? So third hand rule, okay? What I have here is actually one of my favorite kind of physics doohickeys I've come across. Okay, Mr. Van Thiel showed me this. I thought it was so cool. So we have, okay, essentially what this thing is a big magnet, okay? A big magnet with a south pole here and a north pole here, a big flat magnet, okay? Let's test it out to make sure I'm not lying to you, but see, when you put it on top, field lines are up. So what does that mean? They're leaving here, right? Must be north, okay? And then when you put it underneath, same thing. They're going up, so they are entering south there, right? We have our, okay, you can kind of see it flip. So north pole up here, south pole down here. So what does that mean? What is the direction of the magnetic field lines on top? How would we show that with our hand rule? Okay, well, they're going to be all up, right? Field lines go from south to north and then back around to south. So at this point here, the field looks like this. The magnetic field is going up like this. Let's try and apply, that's the first ingredient to our third hand rule, okay? So in our third hand rule, we also have a moving charge. The difference in the magnetic field that we just talked about compared to the first and second is in the first and second, those magnetic fields were induced by a moving charge. Now we have a magnetic field whether there's a moving charge or not, okay? And that's the one we're interested in. We're going to call it an external magnetic field, okay? What's the other part? We have either current or not either. We have currents and moving charges, right? So what is going on here? You can see, okay, or maybe you can't, but I have hooked up, okay, a wire to kind of just a stud on there, right, and on here. So If I were to hook it up to the battery, the circuit would not quite be complete. You'll notice there's nothing in there conductive. This is actually all wood, right? So this is conductive, this metal, this is conductive. You essentially have two parallel plates, but there's no way for charge to actually go across. Okay, charge would not be flowing. What I can use though is this wire. Okay, I can use this wire to complete the circuit. I don't have it hooked up to the battery yet, okay? But let's just think about this. So I have this black one, I will hook that up to the negative terminal, okay? And I'll hook the red one up to the positive terminal, okay? Let's just think for a sec. So electrons are going to be, I'm just going to tilt it a bit, there you go. Electrons are going to be coming, they're going to be on this plate, okay? They're going to then travel to complete the circuit. They're going to want to travel across this wire, right, to get over here to eventually make their way to the positive through the red wire back to the positive terminal of the battery, okay? So how do we make this? So how do we use our hand rules to predict what's going to happen here? First of all, let's think about it in terms of electron flow, okay? You can do current if you want to check my work. I'm going to do electron flow. So where are electrons going to come from? They're going to come from this negative terminal, okay, into the black wire onto this section of the plate. Okay, so what should I use? Electron flow, left or right hand? I should use my left hand, okay? Negative charge always gets a left hand. So the thumb in our third hand rule is the direction of the charge. So where the direction of the motion of the charge. So where are the electrons going to be coming from? They're going to go in there. Then in the portion we're interested in, perpendicular to this magnetic field that's up, right? They are going to move that way. Notice perpendicular, right? 90-degree angle. Here's the electrons moving. Here's the magnetic field up. So according to that, what is the direction of the force this wire is going to feel? So as the electrons come across this way, away from the camera, right, towards me, okay, and the magnetic field is up, according to our third hand rule, see what I mean by you can push, right? You literally push. What is the magnetic force going to be? It should be pushed this way, okay? It should be pushed this way, to my right, your left, okay? Let's see if that's what happens. So if I hook this up to the negative terminal, I always do that. Look at that. Isn't that cool? So it's still hooked up. Okay, no current now because it's not completed. Right? So electrons are flowing this way. Magnetic field is up, so it gets pushed this way. What if I do it not quite as perpendicular? Well, the force is not quite as strong, right? It doesn't accelerate quite as much as we know according to Fm equals QVB, or I guess in this case it's more of an ILB situation. Okay, try using current, but try using our right hand rule. So where would a positive charge flow through this circuit? It would come along the red wire, right? Now it would get here, a positive charge would get here. If this wire allowed it to complete the circuit, right, it would go across that way. So in this portion here where we're interested in, with my right hand rule, now charges are coming at you. Magnetic field hasn't changed. That's still up, right? This is still the North Pole. So magnetic field's still up here. As it goes across, what does our right hand rule, if we were thinking of this in terms of current, say? Says it should be pushed that way. Should be pushed that way. Let's see, does it? Same thing, so it doesn't matter, current or electrons, as long as you're being careful with your hand rule. Okay, but that's because we're no longer dealing with current or electron flow. We are literally going to be dealing with, no, this is a positive charge or a negative charge, okay? There's not the option of thinking about it both ways. But that's not applying here yet, as you just saw, okay? Now let's think about what happens if I switch the circuit around. So now I'm going to unhook these, okay? And instead of putting black on negative and red on positive, I'm going to flip them around. But first, let's see, does the hand rule predict it correctly? So let's go back to electron flow. I'm going to switch it though, so that electrons are now going to come through the red one, because I'm going to put red on the negative terminal, right? So red is hooked up to this far side, so electrons are going to flow from here. Okay, that means now electrons are going to be flowing, so I'm going to use my left hand rule because negatives. My electrons are going to be flowing now towards you. Magnetic field is still up. So what should the direction of the force be? Wherever your palm pushes to, right? So it should be pushing off this way, pushing off this way. Okay, so the left-hand rule predicts it'll go that way. The third left-hand rule predicts it'll go that way. What about the third right-hand rule? Well, current would do the opposite. It would come at me, magnetic field still up, and the third right hand rule also predicts that it should go this way. It should feel a push this way. Let's see. So now I'm going to switch them up opposite way it was just a moment ago. And look at that. So does the, just changing the direction that electrons are moving causes the force to be in the other direction. How cool is that? Okay, so now that we've seen that it works, let's try some examples with it and get comfortable with it.
Here we're using direct current, which we know to be the movement of a negative electrical charge, namely electrons. So we're going to use our left hand. We know that the current flows in this setup from the black wire to the red wire, so we point our thumb to our left. We can see that the north pole is at the top of the screen and the south pole at the bottom of the screen, so we take our fingers and point them out of the screen. This leaves our palm pointing down, and that should be the direction of the force. Let's see. Okay, let's switch the direction of our wires, changing the direction the current flows. Exactly as we expect, since our palm now points up, so too the thing moves up. If we try it over and over again, we'll get the same result.
So let's just start with the first one on page 11, okay? And it asks us in this one, what is the direction of the force for all three of these? Okay, so you can probably kind of figure it out by looking at the deflection, but how can we get there on our own? Well, okay, here we have, look at that, current I, right? Current equals 0. So if I were to take the right hand rule, because it's the current, if I'm looking for the force, what is my thumb? Well, it's not moving, right? So it's kind of like this. So there is no motion. So of course there's going to be no magnetic field, right? If Fm equals I times the length of the wire that's perpendicular to B, okay, and I is 0, then of course the magnetic force is also going to be 0, right? When I had that thing hooked up, if I didn't have current running through it, the wire didn't start sliding down the thing, okay? This is a good picture too for visualizing what it means by the length of the wire that's perpendicular to the field, okay? Does this whole thing count as L perpendicular? No, right? What is the length of the wire that would be perpendicular to the magnetic field? It would just be this part, right? Because it's in the magnetic field. So this whole part happens to be perpendicular, but that's also the whole part that's only in the magnetic field anyway, right? Okay, let's look at this next one. So we have current moving this way, current's going that way, okay? So current would be moving along this direction, okay? The current would be moving along that direction there through the wire, right? We have the magnetic field be in, so they told us in, but we could also figure that out by looking at the x's, okay? Now, current, left or right hand rule, we're going to use our right hand rule. And so current is positive, right? So our thumb becomes the direction of motion charge. If our fingers are the magnetic field, then into the page, okay, and thumb forward. Sure enough, my palm pushes where the force would go, so you can see I'm pushing that wire to the left. So if we ran a current through this wire in this magnetic field, we would see the wire deflect to the left. Okay, finally looking at this one, now current is flowing the other way. You can see current, right? Always check if it's current or electron flow, but in this case it's current, so current is coming down, okay? So take your right thumb, point it in the direction of the moving charge, fingers become the magnetic field. Once again, it's into the page. So when we set it up that way, with our palm points, we push in the direction that the magnetic force will cause a force, so it pushes off to the right side of the page, okay? So this wire would deflect to the right side of the page like they've shown there. Okay, this one asks, what is the direction of the magnetic force in each case? So here I have a positive charge, okay, so that's going to be which hand rule? The right hand rule, okay. It is entering this magnetic field that is into the page, okay, and it's saying which way will the force will be. So we have our magnetic field into the page, we have our charge direction, our positive charge direction moving this way. So for our right hand rule, take your right thumb, be the charge, and then our field is into the page. So which way, what direction will the force be? It will be up towards, I shouldn't say up, it'll be towards the top of the page, right? So Fm would be, let's look at this one. We've got magnetic field. It says up. It should really say towards top of the page. So magnetic field is up towards the top of the page. careful. Now we have a negative charge. Okay, so now we have a negative charge moving that way. Okay, so negative charge going into the field at that angle. What will our magnetic force result as? Well, we take our left hand this time because it's a negative charge, make our thumb the direction of motion for the charge. So that's going to look like that. And our magnetic field is our fingers. So those point towards the top of the page. And what will our resulting force be? Well, it'll be pushing up. So this charge would deflect. This charge would deflect like this, right? It would come towards us. It would come towards us in that field. Okay, so we'd have that, and what would the resulting force look like? Resulting force would look like that coming at us. So how would we represent that on flat paper? We would draw a dot. So F, okay. Looking at C, we have the magnetic field to the right side of the page. We have a positive charge, okay, positive charge moving that way into the field. Now notice here, what is the perpendicular component of this thing's motion relative to the magnetic field? So in other words, if I have the motion this way of the positive charge and the magnetic field this way, what's the perpendicular component of that velocity relative to the magnetic field it's going to enter? Well, it's zero, right? It doesn't have a perpendicular component. It is anti-parallel, we would say, right? The angle between them would be 180, not 90, okay? So they do not have a perpendicular component. So what kind of force will this feel? This will feel no force because no perpendicular component of V. Okay, now this one. There is a perpendicular component. Is it all of the velocity? No, right? So we have a positive charge moving that way. But notice there is some component of the velocity that's going to be perpendicular to the field it's entering, right? If I have V like this, and it's entering a magnetic field like this, then the perpendicular component of its velocity would look something like that, right? Its parallel component would look like that. See how it's parallel to the field line there? Okay, and they even tell us that this angle is 45 degrees. So to get the perpendicular, if we were actually asked to do math with this, which we're not, but it helps to think about it, right? If we were actually asked to do math with this, we would have to take V sine of 45, right? That's the angle it makes with the magnetic field as it enters. V times sine of 45 to get the perpendicular component, and then we could do Fm equals QVB, right? QV perpendicular B, okay? Does this mean it doesn't experience a force? No, it just means the force is not as big. So if we we're kind of going to do this with a hand rule, we would take our right hand, because it's a positive charge, make that be the direction of the charge, and then notice, okay, we can put our fingers kind of off like that, and so it just is that it's not entirely perpendicular. However, it does have a perpendicular component that's just not as big, right? If I had another thumb, you could kind of say, well, there's its perpendicular component. So it does kind of have, it is going to have a force, it's just not going to be as large, right? So as we go from, if just ignore this example for a sec, as we go from here to here, right, the magnetic force goes from no magnetic force when the charged particle moves either parallel or anti-parallel, if I could twist my thumb around, to the magnetic field, right? But some magnetic force when it's somewhere in between, and then the maximum magnetic force that it could feel with that speed when it's at a 90-degree angle, okay? So yes, there will be a magnetic force. It will be in the same direction. It just won't be as large because the perpendicular component is not as large as if it were down here, right? So we have some perpendicular component. You can imagine I'm going like that and saying, okay, that's V, but then there's some V perpendicular, V parallel, right? So that's kind of what I'm saying. It's not that there's no magnetic force, it's just that it's going to be smaller than if this entire V were perpendicular. Instead, just a component of V is perpendicular. See what I mean there? All right, so anyway, still a magnetic force and still in the same direction. Again, just not as large. Which way would it be? Well, positive charge, so fingers are the magnetic field. Okay, this is the direction of the charge, and we see that if I line them up, then the force would be down into the page. I shouldn't say down, into the page, right? So what would the magnetic force look like? It would be an X, right? Tail feathers of an arrow, Fm into page. So again, the speed doesn't have to be entirely perpendicular to feel a magnetic force. It just has to have some component that is perpendicular. If it is entirely parallel like this, then it has no perpendicular component, and then yes, it will feel no magnetic force at all. Okay, example 4 on page 12 here, it's asking what will happen. So we got to get inside the mind of this kind of setup here. So we have a positive terminal here. Okay, we have a negative terminal here. Let's start here just for fun. Okay, what's going to leave the negative terminal? Well, electrons are going to leave that negative terminal, flow through here to get to the positive terminal. Okay, so let's do electron flow for fun. We have our negative charge then. Okay, it's saying we're interested in this scenario here because that's where there's a magnetic field and a moving charge. So if I take my left hand for electron flow, where are the electrons moving from? They're going and then they're coming kind of at us, right? Okay, so kind of at us, not worried about the magnetic field yet. And then what is the magnetic field doing? Well, a magnetic field will go from north to south, right? It'll leave north, enter south. So the magnetic field there looks like that, or up towards the top of the page. So I have my charge moving that way, my negative charge moving that way, and my fingers up. So what will the bar part of the conductor here do? It will go kind of in towards the back of this magnet, right? So FM would be like this, towards the back of the magnet. Okay, and then again, this is a good place to think about this. I wrote down this equation, L perpendicular. Looking at this picture, can you physically see what L perpendicular is talking about? Right? So is it from here to the whole part of that wire? No, right? Because these parts of the wire from here to here and from here to here aren't in the magnetic field. So if we look at this from the side, right, you'll notice, okay, here's the south, here's the north, here's the whole kind of wire part going through, but this is not part of L perpendicular over here. Neither is this. L perpendicular is just from there to there. Okay. All right, a cool kind of practical application of this third hand rule. Okay. There are lots, but this is a cool one. We have basically a jet ski, okay, or some kind of watercraft. How does it work? Well, it shoots water backwards, okay? So use your hand rule to kind of think about how this works. Notice how it must be seawater. Why seawater? Seawater contains, what does seawater have that fresh water doesn't? It has salt in it, right? So salt. If you've taken your chemistry classes, you'll know that salt would be a solution of sodium ions and chloride ions, right? Or whatever ionic compounds, whatever salts, right? So seawater contains ions, so charges. Okay, we have electric charges in the water here. So how does this thing work? It has two, look at these, two oppositely charged parallel plates. So a little bit of chapter 11 at play here, okay? Now imagine you're a positive charge. So for example, let's say a sodium ion that's floating around in the seawater. What are you going to want to do? What are you going to want to do? You're going to want to go from that positive plate to that negative plate. So we have in here two oppositely charged plates, right? Now, a positive charge is going to want to go over to the negative. So when it enters this electric field, it's going to want to move that way. So now we're giving a positive charge of velocity towards the negative plate. It also has a magnetic field applied, so you would have a north pole down here and a south pole up here so that the magnetic field is up. And what happens is it pushes the ions in the water out backwards, right? It pushes the ions out backwards. And then we have Newton's third law. We push the water back, push water back. And when you push the water back, what does the water do to you? Okay. Now you might be thinking, hey, I took chemistry. There's not just sodium ions in salt water. There's also chloride ions, and those are negative. Right, I agree. Take your left hand. Okay, if you're a negative charge, what are you going to want to do in this electric field? You're going to want to go that way, right? If you're a negative charge, you're going to want to do the opposite of what they've got set up here. So, okay, great. Magnetic field hasn't changed. It's still up. So what will you do? Same thing. So if you tried to take these and drive them in a freshwater lake, it would not work as well anyway, because there's nowhere near as many charged particles, as many charged ions in freshwater. You'll notice here MHD, what does that stand for? It actually stands for magnetohydrodynamic, which is a great name. It kind of breaks down all the physics. So magneto, that part's kind of obvious. There's a magnetic field. Hydro requires water, right? If you're thirsty, you need to hydrate. Dynamic, what did we study in physics 20? What was our dynamic unit all about? Forces and how they cause motion, right? So magnets, water, motion. Now, this entire concept, this entire idea that a moving charge in a conducting wire will experience a magnetic force and then cause motion is the entire reason that motors work. So this is actually often called the motor effect, right? Because this phenomenon was used to make the first motors. Okay, this was the first major application of this magnetic force that was perpendicular to the two other vectors. So how does it work? Well, it's all just hand rules. So I want you to be, they've used current, take your right hand, be a positive charge as you move around. Okay, so here we have a magnetic field. As always, field lines leave north, enter south. So as always, field lines leave north, enter south, right? And you can see them doing that there. Okay, on the other side, they're kind of like that. Now, if you're current, you can see, so how would we hook this up? Well, so how would this look hooked up to a battery? We would take it and hook it up to a positive terminal, always the bigger one, right? And a negative terminal, always the smaller one. Okay, that's the kind of the symbol for a battery. Bigger terminal is positive, smaller is negative. So positive charges leave, the current is going to leave. So take your right thumb, okay? So in this portion of the wire, what are you doing? You're going up or towards the top of the page. I keep saying up. Okay, you're going towards the top of the page. So your right thumb should be like that. Where should your fingers be? They should follow the field lines. So what is on this side of the wire? How is that shaft? What is the wire going to feel? What kind of magnetic force? Well, over here, right, on this side, the magnetic force will be into the page. So this thing's going to, on this side, it's going to kind of go like that. Okay, but now you notice the current keeps going. And then it's over here, it's coming down. It's going down or towards the bottom of the page. Okay, so now the current is going down towards the bottom of the page. So take your right hand. Okay, you've got your magnetic field, and now you're going down. So over here, what's it going to feel? Well, it's going to feel a pull out. So down here, it's feeling a push down. Up here, it's feeling a pull out. So what's going to happen if I push down on this side and pull up on this side? Well, I'm going to make it spin, right? And then eventually it gets to where now this side goes. So what do you have? You have something that's constantly spinning just by the fact that you've run a current through it and there's a magnetic field there. So you have a moving charge in a conductor causing this rotating thing. Now, if you attach that shaft to some kind of thing you want to move mechanically, there you go. You have a motor, right? So what have we done? We've taken electrical energy and we've converted it into mechanical energy. That is what a motor does. So you have electric energy and the moving charge, right? Ends up causing a force through this magnetic field interactions, and then that force causes motion, and there you go. Now you have kinetic energy, mechanical energy. Here is just kind of a top view. So now we're going to put our eye up here. So we're looking down on it, right? And the same idea, take your right hand rule. If you are right, so here you're looking at this part from above, you're seeing the current come at you, right? So the magnetic field fingers go that way, current's coming at you, and sure enough, you're going to feel a force that way. So this thing's going to get pushed like that over here, get pushed like that over here. Okay, then over here, it makes its way across, and then it's going down. So it makes its way across, and then it's going down away from you. So now take your right thumb, right? Keep the magnetic field still going that way, but your right thumb's now going down. What's the force? Down, right? Okay, good. That makes sense. So not only is it feeling a push up over here, it's feeling a push down over here, and so you get motion, okay? Electrical energy being converted to mechanical energy. All you got to do is hook that up to something you want to make move, right? And so same exact example here. I'll let you kind of look at this one, play with it in your mind, use your hand rules, figure out how it works. Try your left and your right hand rule, see if you can explain it both ways. Okay, so we use current on the other one. I know they've given us current here, but let's mix it up. Let's use electron flow instead. What would electrons do? They would leave this negative terminal, right? They would go up here, and then they would eventually be doing, obviously, the opposite of what a current, what a positive charge would do. So this would be E minus flow, okay? Now, in this part, electrons are going to go that way. They're going to zoop around, and then they're going to be going towards the bottom of the page that way. So now be an electron, okay? The magnetic field doesn't change because you're an electron, so it's still leaves north, enters south, okay? But take your left thumb now instead of your right, make your fingers the magnetic field, and what kind of force are you going to feel here where the electrons are going towards the top of the page? You're going to feel a magnetic force out of the page, right? A dot. So here you have that as your magnetic force. So this thing is being pulled like that, okay? Over here, what are you going to feel? Well, now you're down. Magnetic field hasn't changed. Your electron flow is down towards the bottom of the page. Magnetic field still that way towards the right of the page. So now you're pushing, your magnetic force will be down X into the page. So sure enough, right, we have this thing being pulled towards us and pushed away from us at the same time. And so we get that motion. Okay, so sure enough, that checks out. That looks right, right, as this thing rotates like that. Okay, this is really just the same image a second later, but try this one on your own. See if you can use your hand rules and figure out, label where the force is and why it makes sense.